Okay, Assalamualaikum warahmatullahi wabarakatuh. We continue with chapter number 3. So we want to see the conformation or the isomer of the macromolecule. Okay, so here we will examining the variation of microstate. Okay, so the conformation of this macromolecule in the process gaining some insight into the nature of certain type of global state. Okay, and here we rely on simple polymer model. This one is from polymer physics for the more complex molecule, macromolecule. Okay, so these are the example of some simple molecule, the N-butane. Okay, so we have CC, and if we see from here, we see that this one CH3, same, and this one CH3 at this side and this side we have 60 degree different, and for this side which is 120 degree different, and this side you can see that it's 180 degree different. Okay, so here we can see that these are Gaussian, trans, and P Gaussian. Okay, so we can have this conformation or configuration for this N butane. So it's either N Gaussian or trans. Okay, so this one is trans Gaussian left or Gaussian right. Okay, okay, so this is Gaussian left, this is Gaussian right. Okay, the electronic structure of the CC bond restrict rotation around the central bond. So this one restrict, so that the molecule will spend most of its time in these three configuration. Okay, so dia tak ada yang 59 degree, 40 degree, 121 degree, or 60, 120, 180. Okay, in these three configuration, you can have this that degree, but most of the time this is in these three conformation. Okay, so imagine that if we have more C, so then there will be a lot more conformation or configuration. Okay, so here for N-butane, the trans and Gaussian configuration differ in energy by about half of kilocalorie per mole. Okay, so if it's trans, half, and Gaussian, half. So if we took the boson distribution, so if we have 100 N-butane, so how many will be in the trans conformation and how many in Gaussian conformation? Okay, so we can take this Boltzmann distribution. So give the relative abundance of the two states in terms of the energy difference. Delta equal to E Gaussian minus E trans, as the property of this G Gaussian right, Gaussian left of trans equal to exponential minus delta E over R T. Okay, so the Boltzmann weight from our thermodynamics, Vt equal to 1 and W Gaussian equal to 0.43. Okay, so we can put it here. So you can see here the property of N-butane being trans or Gaussian are, so we can calculate or we can estimate how many is in trans and how many in Gaussian. So here see that 0.54 is trans and 0.46 is Gaussian. Okay, so imagine that if we have 100 N-butane, so 54 of N-butane is in trans conformation and 46 in the Gaussian conformation. Okay, so this one D2 is referred as degeneracy, like in our quantum mechanics. The term used for account of the of the energetically equivalent variant of a state. So as E Gaussian gets larger, Wg, the weight gets smaller. So P Gaussian approach 0 and Pt approach 1. Okay, so if Eg is large, so from here, this Ea, G, so it's only minus T. So we have all out of 100 N-butane, so all are in the trans conformation, no in Gaussian conformation. Okay, so when RT is small compared to the energy difference, a molecule spends most of its time in the lowest energy state. Okay, so the lowest is minus energy, minus energy. Okay, so we can have this. Okay, so if we calculate the mean N to N distance of N-butane, so we want to if we want to calculate this length, okay, between this C and C. Okay, so we know that is L bar equal to LT PT plus LG PG. So where LT and LG is length of trans on Gaussian conformation, the width of between C and C. PT and PG is probability of trans and Gaussian conformation. So and to avoid L equal to 0, suppose not P0, we use a root mean square to calculate the length. So square root of L squared bar equal to L squared T squared PT plus LG squared PG. Okay, so we have this length. Okay, average length of this N butane. Okay, so this one is our statistical physics from our statistical physics function and polymer chain. Okay, so we have this polymer chain. So for a molecule with N state, the partition function is equal to Q equal to either this equation 1 to N exponential minus EI over RT, or the weighted density of the state with energy E omega E exponential E over RT, where the mean energy is equal to RT squared D ln Q over partial T. Okay, so we can get uh, this partition function. This is from your statistical physics. Okay, so these are example. So relation between a polymer is a very long chain, and it consists of monomer, the the basic part of this polymer. So if we have a chain of n monomer, and each monomer can have a different energy, and we do not denote the energy of the n monomer as En. So even the monomer are independent out of each other, so the molecular weight for a particular composition is equal to the product of omega En exponential minus En over RT for each energy, or for each monomer, so multiply for each monomer. Okay, so we can get this particular elementary weight for particular configuration. Okay, so the partition function can be written as this equation. So here we can see that all the monomer we've had with energy 1, we do the summation, and we have this number. And the energy, the monomer with energy 2, we have this summation, and until the monomer with energy n function, this summation. Okay, so we multiply all of this partition function, so we can get Qn equal to Q1 n to the power of n. Okay, So if the monomer are independent, then the partition function of the polymer is just the partition function of an isolated monomer raised to the power of n. Okay, so uh, we take the monomer, one monomer, okay, one partition function for the monomer powered by how many monomer that we have in the system or in this polymer. Okay, so next we have a random coil. Okay, so we have a very long polymer, or we have a very long macromolecule, but because of the molecular force that from our chapter number 2, so it will do the bending and stretching. So we are going to have uh, uh, a very short or a very compact figure of that polymer. Okay, so these are flexible polymer chain such as polyethylene tend to bend, okay, because of that the molecular force, and the coil randomly, maybe because of hydrogen bond. So we can do the modeling of how small or how they uh, put it together, or they pull together as a polymer. Okay, so we have three model here. So we have the freely jointed chain, where each segment has a complete freedom to rotate and any angle is equally probable. Okay, so macam contohnya macam kita punya lengan dengan siku. Okay, so kita boleh gerakkan kita punya lengan dan siku ke semua arah yang kita mahu. Okay, so any angle is equal. Next is the freely rotating chain model. It has a fixed bond angle, but the dihedral angle can assume any value. Okay, so here macam kita ada tangan kita, siku ataupun siku kita kena simen. Okay, so kita tak boleh gerakkan siku kita cuma boleh gerakkan bahu kita. Okay, so if we fix this bond angle. Okay, and then the rotational isomer model has a bond in like and butane, for which the angle have a few favored value. Okay, so this one macam N butane, contohnya 60, 120, 180 angle. Okay, so the rest we cannot uh, it cannot take the rest of the angle. Okay, so first we see the freely jointed chain. So we can see here these are C, 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 C. Okay, so we want to know the initial end to end distance. So kalau dia boleh datang ke sini balik. Okay, so we have a loop, but here we can see that these are the end to end chain. So if we do the calculation, because Rn contohnya R1 tak sama dengan R2, R3 tak sama dengan R2. Okay, so we do the summation. So Rn, the n to n vector, Rn equal to the summation from n1 to n Rn. Okay, so we have the n vector, this one. Okay, and the freely jointed chain, so to avoid Rn equal to 0. Okay, so kita tak mahu yang Rn ni ataupun this molecule or the n carbon coincide with the first carbon. Okay, so then if that it becomes 0. So to avoid Rn equal to 0, we took the square. Rn squared bar equal to NL squared, where n not equal to m equal to 0. Okay, so here we can say that the n to n length is equal to the number of uh, molecule, the number of carbon, for example, the length of the carbon, L squared, the average length of carbon. So we can get the end to, or we can estimate the end to end length of the polymer. Okay, so it increase as square root of n. Okay, so we have, let's say C6. Okay, let's say C6. So C n equal to 6, so square root of 6 equal to something. Okay, so we can estimate the number of the end to end of that C6 polymer. Okay, so next we have the freely rotating chain model. So we can see here we have this one, alpha, 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 and alpha. Okay, so you can, have this fixed uh, dihedral angle, so you cannot move freely like this with the model before this. Okay, so without any proof, so these are supposed to be our assignment, but because of time, so we can see that this the end-to-end angle, length of this model is equal to this equation. Okay, so in our textbook is 1 plus cos theta 1 minus cos theta L squared n, or in this case 1 plus cos alpha 1 minus cos alpha L squared n. Okay, so we can calculate the length, the end-to-end length of this n to this n equal to this equation. Okay, so we decide what is alpha, so we can get, or we can estimate the n or to n. So next is the rotational isomer model. The root mean squared length is equal to theta 1 plus cos theta 1 minus cos theta, and 1 plus cos p 1 minus cos p. Okay, so this one is there is moving around, and then we can do the rotation about the 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 molecule. Okay, so we can get this n to n, or the root mean squared of n to n length is equal to this equation. So if we know the theta and we know the p, we can calculate the n to n length of that molecule, or we can estimate the length, n to n length of that polymer. Okay, so next is we have the effective segment length. Okay, so this one is, if we have uh, a very long polymer. Okay, so we can estimate, or we can simplify for it, one segment. So we have a length, end to end length for this segment, end to end length for this segment, end to end length of this segment, and end to end length of this segment. Okay, so this one is effective segment length, or in other words is Kuhn segment. So the Kuhn segment is equal to Rn squared equal to L effective length squared n. Okay, so rather than using this length, this length, this length, this length, this length, so we have this effective segment length. Okay, so we can calculate the end to end length using this effective segment length. Okay, so here if we have L effective greater than L, then we are saying that the molecule is flexible. So contohnya macam rantai. Okay, so kita boleh main-main dengan rantai tu, dia boleh berbentuk macam-macam komposisi. But if L effective is greater than L or greater than this L, small l, then the molecule is stiff. Okay, so maknanya the end to end length will be much longer. Okay, so sebagai contohnya macam kita ada rantai yang tak boleh ataupun kita punya badan. Okey, kita punya badan. Okey, kalau kita punya badan tak lembut, so kita kalau kita buat exercise tu, kita punya kepala tak dapat menyentuh kita punya lutut. Okey, ada setengah orang boleh sampai sentuh lutut, tapi kalau badan kita keras, kalau kita memongkok pun kita tak akan sampai ke kepala kita tak akan sampai mencecah ke lutut. Okay, so that is the stiff one. Okay, so next we have this conformal flexibility characteristic ratio. So C equal to this L effective Z over L. So where Z is a geometric vector used to account for the fact that a fully extended chain may have a length less than N L. Okay, so because of this L effective, so we estimate when we using that tree model. So we have end to end length, but when we have this when we do the experiment, so we have a very a longer length or a longer end to end length than the modeling. Okay, so the characteristic ratio tell us how much longer the mean square end to end distance is than it would be if it were a freely jointed chain. Okay, jointed. So it will be much longer. So these are the some of the value for common polymer. Okay, so here you can see that L is 1.54 between C and C, the monomer and the monomer. But L effective, the Kuhn segment 12.4. Okay, maknanya contohnya ini adalah untuk setiap 11 monomer, so we have one effective length. Okay, Z is the factor 0.83, C is 6.7. Okay, so it's a long. Kalau contohnya polyethylene ini, kita katakan the end to end root mean square dia adalah 1 cm, tapi sebab oleh this stiffness, okay, so it will be 6.7 cm. Kepanjangnya akan jadi 6.7 cm. Kita kata 1 cm, tapi sebenarnya 6.7 cm. Okay, so this also you can see that 3.8, so 9.0. This one is 86. Okay, so these are longer. Okay, so next is we have the persistent length, LP. Measure the polymer stiffness, LP equal to this equation, or in this characteristic ratio, LP equal to LEF over 2. Okay, so this measure the polymer stiffness. So how stiff is the polymer? Okay, so kalau polymer tu keras dan rapuh, so kalau kita nak buat measurement the pressure, so we must be very careful with the pressure we put into the polymer. Okay, so next is the non-ideal polymer chain. Okay, so kalau polymer chain, ideal polymer chain semuanya sama, tapi dalam in the real life there is no such thing of ideal chain. Okay, and also we have the theta solvent. Okay, so here first we see that non-ideal polymer chain. Two other interaction that influence the conversion of molecule are attractive interaction. Okay, so here we can see that kalau polymer ideal chain dia tak ada interaction. Okay, these two. So here you can see that attractive interaction such as hydrogen bond and hydrophobic force will pull distant segments together and tend to make a chain more compact. But kalau yang ideal polymer chain, so it less compact. Then we have the steric repulsion, which prevent two segments from occupying the same space at the same time. Okay, so maknanya C1, let's say C2 and C5 cannot be stay together in the same coordinate. Okay, so either C2 must get out from that coordinate, then C5 occupy that coordinate, or C2 is still at the coordinate, so C5 will not be able to occupy that coordinate. Okay, so for ideal chain, so we can see that root mean squared is equal to square root of n, but for non-ideal chain, excluded volume, so we have n equal to the root mean squared is equal to proportional to n to the power of 3 over 5. Okay, so what we can say is that the absolute volume effect tend to increase the effective size of the molecule relative to that expected to for an ideal chain. Okay, so this one, kalau kita ada dua sphere, okay, so sphere this one is much bigger than this sphere. Okay, and for attractive interaction depends only on the choice of solvent. Okay, so it also depend on the solvent. So this one we want to say is that even though we have the same molecule, but if we put in this different solvent, so it will either do the coil bending, or it will be just a straight line. So if the polymer segment are weakly soluble, then the segment will clump together to reduce the unfavorable interaction with the solvent. Okay, so ni macam bola. On the other hand, a good solvent will make the chain more extended, jadi lebih panjang. Okay, the solvent is called the theta solvent if Rn squared equal to this equation, the freely jointed model is equal to L squared to the power of times n. Okay, so this one meaning that this is equal to cos theta is 90 degree, so we have 1 over 1 L squared to the power of n. Okay, so theta solvent when 90 degree radian, so where it because this cos theta become 0. Okay, so that's all for the first